Hello, Mr. Kaladi here, and today we're going to be doing an introductory lesson to calculus. Now, usually this is covered in the second half of our pre-IB grade 10 program, the rates of change, but I don't believe you did it last year. So I've included it here. It's a little out of order, even though it's kind of an introductory, but we're going to need it for the next lesson, so we're going to go through it today. Calculus is at its core a study of rates of change. How fast is something, like y, changing with respect to x? Now, one way we can look at this is delta y over delta x, which you've learned in grade 9. The slope formula, y2 minus y1 over x2 minus x1. This delta, you guys should know this.
Miss Carlse, call on 101. Miss Carlse, 101. Thank you.
Delta is, you would say, this is a change in y over change in x. And there's the formula. And that's our slope formula. So that's really what calculus is about. It's all about slopes. It's also known as the gradient. Also called the rate of change. So in some ways you're already familiar with the basic ideas of calculus. Let's look at this first example. Sarah rents a car paying this amount of money. So it's a fixed amount, an amount per D. So C is the cost in dollars and D is the amount of distance she drove in kilometers. So she can calculate how much she owes the rental car company. So one way to solve this would be to make a table. So if I drive 0 kilometers, I still have to pay 35. If I drive 100, then I have to pay 35 plus 15, so that's 50. So I could use my calculator in my brain to fill in this table. And then I could actually graph this. So we go up to $400 or 400 kilometers. And the costs go up to, say, 100. And this is 50. 75, 25. So if I were to graph this information, well, we start at 35, which is somewhere up here. Then I go to 50, 200 is 65, etc., etc., etc. What's the next one? 300 is 80, and then 400 is 95, somewhere like that. And if I were to, okay, so that's my my graph showing the relationship between distance and cost. Now, if I want to find the rate of change, well, rate of change is a nice way of saying the slope. And when it comes to straight lines, I'm great at finding the slope because we did this in grade 9. To find the rate of change of this line, I'm going to use the slope formula, which is rise over run. And that would be delta. Okay, the rise is a delta C. The run is a delta D. In other words, it would be C1 or C2 minus C1 over D2 minus D1. There's other ways of looking at this, right? You might have, your teacher probably did with you the idea of rise, run, and they drew a little triangle like this. So in this case, you can see my rise and the run and the points. This one's 100 comma 50, this one's 200 comma 65. So you could figure it out using the graph. I think it's makes a lot more sense to do it algebraically. So I take my second cost, which is 65, minus my first cost 50 over my initial distance 200 minus 100. So I end up with 15 over 100, which gives me 0.15. What does this slope mean? What's this rate of change? Well, the top was cost, so this is dollars on top, divided by distance in kilometers. So this is the dollar per kilometer. In other words, what's the rate of change? Well, the cost increases by 15 cents for each kilometer. So the rate of change, it's a rate. The slope, it's a rate. It doesn't mean how much you pay when you drive 200 or drive 300. It's how much the cost is changing for each change in D. And this is something you guys know from grade 9. It's a slope. The slope's always the same. Use the slope formula, you get your value, and you can interpret. So, our study of calculus in high school is motivated by this question. What is the rate of change, or the slope, of a function? That is a curve, so not a straight line. Because as you kind of imagine when we taught you this, at some point you probably thought, well, great, I can find the slope of a line. How do I find the slope of a curve? And the answer to that question is with calculus. That's what the whole first part of calculus is all about. So let's take an example. A ball is dropped from the CN Tower and falls according to this equation, where S is the distance it's fallen and T is the time. Determine the velocity of the ball after 1 second. I like this question. This is at 1 second. I like this question because velocity, it forces us to know the velocity or speed formula, which kind of keeps coming back in calculus. For those of you who didn't do this with your grade 10 teacher and didn't take physics, this is a new formula, but it's a straightforward one. Your velocity, or your speed, same thing basically, is distance divided by time. Think about when you're driving in your car. If you're traveling 100 kilometers, it takes you an hour. Well, you're traveling 100 kilometers per hour. That's your speed. The speed or velocity is a rate of change, right? This is a slope. Rate of change, or slope. So when I graph this, let's go back to this curve. S is the distance. It's not and this is time. So we're going to get a distance time graph. It's not going to give me the velocity. The velocity is the slope. But let's graph it at least. So S, okay, so at time 0, I sub in 0. So it's 4.9 times 0 squared, which is 0. For time 1, it's 4.9 times 1 squared, which is 4.9. Then for 2, it's 4.9 times 2 squared, which is 19.6. I can keep doing this. I get 44.1 and 78.4. So let me, you know what I forgot to do? I forgot to label this. So this is distance in kilometers. This is cost in dollars. Label my nice graph. So this one, we're going to do time up to 4 seconds. Oh boy. 1, 2, 3, 4. Time, which is in seconds. And then we're going to do distance. It looks like the distance goes up to 80. So this is 40, 60, 20. So this is my distance fallen in meters. Okay, let's graph. So, this is the distance, yeah, we've fallen. So we have 0, 0, 1, which is 5, 2, which is about 20, 3, which is 44, and 4, which is almost 80. So you can see this, no surprise, is a quadratic, right? Because it was a quadratic equation, and the graph should look more or less quadratic. That's my distance time graph. However, if someone asks you for the velocity, they're actually asking you for distance over time. They're actually asking you for the slope. So let's look at this, excuse me. So if I look at this question, what is the slope? Well, the answer is it's complicated, right? It depends on where you're talking about. The slope at this point is different than the slope at this point. The graph is steeper later on. It's a lot flatter early on. So when you say what is the slope, it's kind of a loaded question. To set us up for tomorrow's lesson, I want you to think about rate of change we can think, there are two ways we can think about slope or rate of change on a curve, or that is on a curve where the slope is constantly changing. One way we could find the rate of change is to look at the average rate of change, or the average slope, basically. Or, in this case, we're looking at the average velocity. So remember this graph, it went up to 80. So sorry we have to draw it again, but oops, oh well. So it was looking something like that. So one way of figuring out the slope is to find the average. And the average you would find by taking any 2 points that you know on the graph. So let's say you want to find the velocity at point number 1. We're going to choose, sorry, at time equals 1. We're going to choose 2 points that we know on the graph. So let's use point number, let's use this point at 1 second and this point that we know at 4 seconds. We're going to draw a secant line. We're going to call this secant A. A secant line touches the curve at 2 points. So to find the best guess for the slope at t equals 1, I'm going to use the t equals 1 point and the t equals 2 point. Now I can find velocity secant A. So I'm going to find the change in the rise and run, or the rise over run, or the change in s over the change in t. So just like I did last time, just using the slope formula. So this point is 78.4. Subtract the y value here, which is 4.9. And then the t, I take 4 and I subtract 1. Type that into my calculator. 78.4 minus 4.9 divided by 3 gives me 24.5. Distance was in meters, divided by time was in seconds. So my slope, or my velocity in this case, my best guess at point time equals 1 is 24.5. Now that's not bad, but I can tell that this slope is not the same as kind of the actual slope. It's a bit steeper. So you might say, well, maybe instead, what would have been clever would have been to have taken, instead of using point at t equals 1 and point at t equals 4, I should have used the point at t equals 1 and the point at t equals 3. So I'm going to get a different color. I'm going to draw a second secant line. Oh, that's not a great color. Let's use blue. It's a little easier to see. My Muji pen betrays me. So there's my secant line. I'm going to call this secant B. Secant B already looks a little better. It's a little flatter. It's a better estimate. So let's figure out this velocity line B, or this secant line B. Again, it would be rise over run. And that's going to be, okay, so this point, if I go to the back, it was 44.1 minus 4.9 over 3 minus 1. Let's do that. 44.1 minus 4.9 divided by 2. That gives me 19.6. That's better, right? That's a little flatter. Is that my actual average, or my best approximation for speed? Well, it's not bad, but again, this question would probably even be better if I had used this point, the nearest point. Okay, I need a different color. This isn't going to work. Muji pen, you've betrayed me. Oh, I've got one here. It's green. Perfect. We're laughing. It's also Muji. Okay, let's find this secant line. We'll call it secant C. Now, again, I'm probably not going to get you to do this. This is more just looking at the process of of how the calculus works. So 19.6 minus 4.9 over 2 minus 1. So 19.6 minus 4.9 divided by 1 gives me 14.7 meters per second. So if you look, I would say secant C is better than secant B because it's a little flatter, but it's still not perfect, right? It's still, you're only as good as the points you've been given. So that's the great thing about the secant line, that you can do it using any 2 points, but the bad thing is it's not perfect. This would be the equivalent of, if I were to drive from here to Windsor, and I noted how long it took me and how far I traveled, and I divided them and found the velocity. That would give me my average speed, right? My average rate of change. It's basically finding a secant line. It doesn't reflect that, well, when I was in Toronto, I was going very slow, and then when I got outside of Toronto, I was going very fast, right? The average only gives you information based on the start and finish, or 2 points. It doesn't know what's happening in between. So it's imperfect, but it works. Let's go back to the original question. How do I find the slope at a specific point? One option was the secant line. The second option is to find the instantaneous rate of change. That is the instantaneous slope. Or in this question, that would be the instantaneous velocity. To find the instantaneous velocity, we need a tangent line. The tangent line is a line that just touches the curve at one point. Okay, let's take a look. Let's graph this again for the 100th time, basically. Okay, and then we have 0, 0, 1, 20-ish, 44, and 80. And I'm going to draw this nice curve. There it goes. Okay, watch how the tangent line works. So if I wanted to find the tangent line at t equals 1, the slope at t equals 1, I draw a line that best approximates the slope at that second. And to do that, you draw a line that just touches the curve at that point. Now you have to try to balance it so that it is the best approximation. Your sketch is never going to be perfect, but you're going to have to do your best. I always think, when I teach tangent line, I always say they think of it like a skateboarder, when they kind of go down, they grind on something. The skateboard hits this and it kind of follows the arc of that thing that the skateboard's riding. So this is an upside down skateboard, but when you graph it, you kind of get the tangent line, maybe something like this. Now, using my tangent line, so there's my tangent line. Again, yours is going to look yours is going to look slightly different than mine, but the point is that it's a line that just touches the curve. Tangent. Now, you choose 2 points on the tangent line. Try to read them off of your graph. For convenience, I have 0, 0. Doesn't always work out like that. And here, this is what, 319 maybe? I don't know, something like that. If you do your best to read it, it would have been better with graphing paper. To find the velocity of the tangent, so v tangent, I now find the slope of this tangent line. So again, it's rise over run. So I have 19 minus 0 over 3 minus 0. That gives me 6.33. Just put 6.3. So, and again, that's our best guess. And if you look, again, it's a pretty small, it's not too far off, but this we knew was not correct. Now, what's the problem with the tangent line? Well, the problem is my tangent line and your tangent line are probably slightly different because we just made it approximate, right? So your angle could be slightly off. It could look different. It has to do with how you drew the graph. It's not reliable because we're drawing something and then interpreting it. So that's why this number is not super reliable either. So I have, I think I summarized that here. We do not like drawing a tangent line because it's not accurate. So I have these two methods of finding the slope. They're both they don't really do it. They don't give us the best number for the slope at this point. We are going to learn to use calculus to do this. But for now, yes, or soon we will be able to find this instantaneous rate of change. We'll be able to find the slope of the tangent line with calculus. But for now, we only know how to do it by drawing. For now, then, if I had to ask what's the best way for finding slope, I would say it would be to take 2 points and finding the average between the two of them, finding the secant line. And which 2 points? Well, choose the 2 points that are closest together. In fact, for now, we observe that the secant line is a good approximation of the tangent line if the delta x is very small. That is, for this lesson, where we'll end it, is the best secant line is the one where these 2 points, these two x values, are close together. I imagine as this point gets closer and closer and closer to x equals 1, this secant line becomes closer to my tangent line, my real tangent line. Preview. That's what we're going to be learning in our next lesson. For now, I want you to be more comfortable with this rate of change idea because I don't think you did it last year. So I would like you to do number 1 and number 3, and I think that will be enough. So yeah, just please do question 1 and question 3. And you're going to have to get to know this idea of secant line and tangent line. I posted the answers on the side. Good luck with that, and we'll see you next time for the big calculus lesson.